Hello everyone, welcome to another video. In this video we will see basic usage of an open source quantum chemistry code based on Python. The benefit of using this open source code, which is PSI4, is that it is open source and anyone can customize it for chemical science analysis. This is written in C++, but Python interface is available and thus lots of customization of the problems are possible with this piece of code. We will see some basic here, and purpose of this tutorial is linked with the follow-up video in this playlist. If you know the basic of PSI4, you can skip this video without any reason. So let's begin. First, let's name this book, and this is going to be our first video in the series, and I like to call it basic intro to the PSI4. I like to have some underscore between the words, and that's a Python style, not mine, but it's very common. Okay, first of all let's import PSI4. PSI4 can be installed from their website, and it's easy. Let me know if you want me to make video on it. Let's run some basic geometry optimization problem on a simple system and understand how the syntax works here. For example, let's run geometry optimization on water molecule. I am writing geometry optimization as geo to save time. Geo is not graphene oxide, it's geometry optimization. Okay, let me clear it. Geometry optimization of water molecule. Okay, so how we define a molecule in the PSI4? It's very simple. You can name it so that you can use it just like a variable. Okay, H2O is equal to how we define it. PSI4 has the geometry function PSI4 dot geometry. I hope it comes with the tab. Yes, it is coming. Okay, how we can write it? We can write it in the Z matrix format, or we can specify atom coordinates, but here I will use the Z matrix. So we can use 3 quotations, and I can write my geometry here. Okay, water molecule has 1 oxygen, 1 hydrogen and another hydrogen. If I do not name the oxygen, or say it's first one, so it is considered as first one, and then in the next for the hydrogen I need to tell that it is connected to the first one and with some distance, and that I am going to use is 96 angstrom, and that's it. And then for the next hydrogen I need to tell PSI4 that it is also connected to the first atom, and distance is 9.96 as well. But additionally, this hydrogen is at a 104 degree away from the second atom. Yes, and how we can specify it? We write second 2 and specify the bond angle, and that's how we can specify the geometry of a molecule. This is a simple molecule, so I can write it, I can type it. Otherwise I can import this geometry from anywhere, from any GUI base or camera base software. Okay, let's go through step by step what we can do this with this molecule. H2O, if I type H2O, it tells me that it is a PSI4 molecule, because we have tell the PSI4 to save these string as a geometry, and PSI4 can recognize this string, this formatted string in Z matrix as a molecule. Okay. Okay, if we want to optimize this, how we can optimize this? We can optimize this molecule simply by just saying PSI4 to optimize it. Optimize, and we can pass the SCF, self-consistent field convergence, and we can also pass the basis set. I'm not going to use higher basis set as my laptop is not that powerful, so I will use the smallest basis set, and I press shift enter, and it runs for a while, and it's still running, and after completion it is saying optimization complete, and it is giving me the energy. To calculate the energy, you can also write PSI4 dot energy, and you can pass your theory. You can pass higher basis at 631 G. Okay, and here is your energy. Okay, we can also do the frequency calculation and save the energy and wave function for later manipulation just by assigning the frequency method to the respective variable. For example, we can make two variable, SCF energy and SCF wave function Fn, and we ask PSI4 to run a frequency calculation, and our theory is going to be SCF with the I'm going to use smallest basis set just to save time. It's not a big deal. And now I need to pass the molecule, and my molecule is going to be water, and that's why it was saved. Okay, if I am writing it correct. Okay, and I also want the frequency calculation to return the wave function, and I can write it equal to true, and here it will, okay, again if I can spell return correctly. Now my frequency calculation is running, and when it's running, when it's finished, it will return the energy and the wave function in the respective variables. Let's see what does SCFE contains. It contains energy and the SCF WFN, which is the wave function. Okay, this is the wave function. We can manipulate it later, and that's how you can perform simple task. You can optimize and get your energy simply, and PSI4 automatically update the geometry of your molecule after optimization. Okay, let's optimize a little big molecule. Let me copy paste a string, because I'm not going to type or everything, just to save time. Molecule, I can define new molecule as a molecule and pass PSI4, call PSI4 geometry, and I can pass my string here, right? And I need to remove this, and I also need to remove this as well. Okay, that's my C2H6. 1 2 3 4 5 6, yes, right, it's ethane, and here it is ethane, and I can run it in the same way. For example, first I run this, and then I need to tell PSI4, I need to call PSI4 dot optimization, optimize, and then I pass SCF and 6631G, and then I need to tell my molecule. It was not the case in the first example because it was clear that my molecules was water. Now now I have two molecules in the workflow, so I am mentioning it now. I can also write same for the energy. I can also calculate energy, and I am just going to save my time just copy pasting, and that's it, and that's my energy. And I can also export it just by calling the global variable of PSI4, PSI4 dot set output file. I can say, I can write any name I want, just like ethane dot dat, and that's it. Just run it. Okay, since I have performed the optimization and energy calculation earlier, so my file will be empty. Let me just open it here with open, and my file name is ethane.dat. I need to pass a string in the write mode, I am sorry, in the read mode. Okay, as text. Okay, it will open as text, and what I'm going to do, I am going to print this text dot read. Okay, let me print it. Print text file, and here is my calculation, and as you can see, it is empty. So what I need to do, I need to do optimization now. PSI4 dot optimize, and I just need to copy this one here. So I have defined my log file, I'm sorry about that. Okay, I just need to copy another code of line here. Now I have set my output file, and I am asking for optimization. Let's run it. Meanwhile, I can rerun this code here, and let's see if it is populated now or not. What? Yes, it is populated. Now you can manipulate this with the help of Python logic you have in mind. Let's do another example and another task, and that is intermolecular interactions. Intermolecular interactions are very important for various properties, and that's why I like to discuss it here. And I will copy paste it from the original documentation, no big deal. This is a CH2 C2H4 and CH3 2H2 molecule. These two molecules are going to be, how they are going to interact, we want to calculate their energy, and I have defined as a dimer. And now I need to set few things like I can pass various options as set options, and I can pass these options as dictionary. For example, I can pass the core, that I need to freeze the core, so it is passed as freeze underscore core as true. Okay, I can set other options if you want, and it depends on the particular problem. I can also, okay, here is the problem, that true do not need to be passed as string. And I can also set the memory for of this calculation, and this is set using the global option set memory, right? And I can give it 2 GB. I have it, I can give it. And I can also mention this time the file name before optimization, and let's set output file, and this time I will name it dimer.dat, so that I open dimer.dat only. And for interaction I don't need to optimize it, I need to just calculate the energy. So I will calculate the energy, and I will pass the SAPT analysis. SAPT analysis is used symmetry perturbation theory. It is used for interaction studies, and I can pass it as a string SAPT0, and I can pass the June augmented basis set. Okay, let's do not pass augmented, just pass the June basis set double zeta, and then I need to tell it that I want to calculate the energy of dimer, and here it is, and let's it run. Meanwhile, I can copy the same option here, and I can paste it. Okay, we have it now, we have our energy here. My file is not ethane this time, it is dimer.dat, and I can see the results. And here is the SAPT analysis. SAPT results are presented in the last, and you can see SAPT results here. It's for exchange, dispersion, and electrostatic interaction, and you can see the you can extract your SAPT results from implementing the logic of SAPT result. Okay, that's how you can perform the interaction energies. And in this video we went through the optimization problem, how to calculate energy, and just by asking the dot optimization dot energy method. And that's it for now. Let's meet in the future videos. Bye.